So next is section 3.7. And it's titled Rates of Change in the Sciences. This is what this course is designed for. Okay. So derivative of y. So we're going to define the units of derivative of y with respect to x. Okay. Is the rate of change of the variable y with respect to the variable x. The units of dy over dx are the units of y per units of x. So it's something per something, okay? And so we experience this, right, in real life all the time. Miles per hour, kilometers per hour, okay? People per square mile, right? Sales per month. We see those kinds of units all the time, okay? So something per something, or it's the units of derivative y with respect to x, okay? All right, so we're going to demonstrate, we're just going to do two examples. So in the first example, a ball launched upward and we've done this type of example already this semester. A ball launched upward is at altitude s of t equal to 64 t minus 16 t squared, right? So that's the function that gives you the altitude, the height of the ball, right? It's a function of time. And the units are meters. At time t seconds after launch. So time starts at 0, right? T equals 0 is launch time, okay? Time of launch. And S of t tells you the height of the ball, okay? The altitude of the ball, t seconds after it's been launched, okay? All right, in A, we're going to find the ball's velocity and acceleration. At time t and the units of each. So let's first find its velocity. How do we find the velocity of the ball at time t? First derivative, right? So V of t is equal to s prime of t. S of t is just quadratic, right? So you differentiate term by term. Derivative 64t is 64. Derivative minus 16t squared is minus 32t. Okay. What's the units of the velocity? Meters per second, right? So, you could think of this, right? V of t, right, is like derivative of s with respect to time, right? Change in height over change in time, right? Height is in meters, time is in seconds. So the units are meters per second, okay? Units are meters per second, okay? And so you can write it out, right? Meters per second. In physics, I think they like, from what I remember from my college days, they like to write it out as a fraction. Meters in the numerator, seconds in the denominator, right? And you could also just do m over s. And then lastly, you could do the abbreviated MPS, right, for meters per second. Okay. All right. You can pick your medicine. Okay. All right. The acceleration. How do we find the acceleration? Second derivative of s of t, or the first derivative of v of t, right? So the acceleration a of t is equal to v prime of t, which is the second derivative of s of t. And the derivative of v of t in this case, right, derivative 64 is 0. Derivative minus 32t is minus 32. Okay. So the acceleration is constant. What are the units?
Meters per second squared.
Say that again.
Meters per second squared.
Yeah, meters per second squared, right? So in words, you could write it as meters per. So let's remind you, velocity tells us how fast the height of the ball is changing per second. Acceleration tells us how fast the velocity is changing per second, right? And so that's why she said meters per second squared. Okay? So it's actually meters per second if you write it out in words, because meters per second is velocity. And so you got velocity, right? So acceleration is how fast the velocity is changing per second. Okay. All right. And you can write that as meters, as I like to do in physics, meters over second squared. And that's meters per second. And then you could also write it as m over s squared, where s stands for second. Okay. And then you could also write out MPS for meters per second, and then add the word per second. Okay. the end of the day, acceleration is how fast the velocity is changing. All right, so the acceleration in this case is minus 32 meters per second. I just realized something. I gotta fix this. I borrowed this problem from another professor. Okay, so you guys know what the acceleration of gravity is, right? What's the acceleration of gravity here on the surface of the Earth? What is it? 1 meters per second, right? So this is obviously not right. What is it in feet per second? Yeah, it's actually 32 feet per second, right? So 9.8 meters per second is equal to 32 feet per second. And so I noticed that I just realized I have to go back and fix this for the future. We got the number for feet per second in a problem where we're saying meters per second. Okay. So, but you know, if I didn't tell you that, no one would know that. Okay. All right. I mean, it's not going to affect the lesson that we're learning from this problem. Okay. All right. So that's the velocity and acceleration as a function of time. So in B, so that was A. In B, we want to know when is the ball traveling upward, and when is it traveling downward? Okay, so I mean, you know, when a ball is thrown up in the air, right, it's going to go up for a while and then it's going to stop and come back down, right? So when is the ball traveling upward and when is it traveling downward? Okay, well, we can answer that question with the velocity function, because when the ball is going up, the velocity is positive. When the ball is coming down, the velocity is negative. So the sign of the velocity tells you whether the ball is rising or falling. Okay, so it's going upward. When V of t is greater than 0, is positive. Okay. When the velocity is negative, it's coming downward, right, crashing towards the Earth. Well, the velocity V of t is equal to 64 minus 32t. So this is a linear inequality. And since we all have excellent pre-calculus skills, we know how to solve that, right? So this is linear. So we just solve for t like you would if this was an equal sign here, right? So we're going to subtract 64 from both sides. We have minus 32t is greater than minus 64. And now I can divide both sides by minus 32. And I have t. Now what happens to the inequality symbol when I divide both sides? Yeah, it gets flipped, right? So I have t is less than minus 64 over minus 32, or t is less than 2. Well, remember, time starts at t equals 0, right? So the time that the ball gets launched upward at t equals 0. So the time that the ball is traveling upward is from t equals 0 up to t equals 2. Okay? So we would write t greater than 0 and less than 2 seconds is when the ball is moving upward. When is it moving downward? When the velocity is less than 0. So again, V of t is equal to 64 minus 32t is less than 0. Okay. And so now, when you solve this linear inequality, instead of t less than 2, you get t greater than 2. Okay. Now, is the ball moving downward when t equals 10? The answer is no. Okay? So here's what you got to be familiar with. S of t here is a quadratic function. And S of t gives us the height of the ball as a function of time, right? Well, at t equals 0, S of 0 is equal to 0. Right? So the height of the ball is 0, right? It's on the surface of the earth. This is a quadratic function. What's the graph of a quadratic function? Parabola. Our parabola is symmetric. Yeah. So S of 4 is also equal to 0. You can verify that, plug in 4 and for t and S of t, and verify that S of 4 is equal to 0. So this is the height of the ball as a function of time. That's supposed to be a symmetric parabola opening down. The number in front of the t squared is negative, so the parabola opens down. Okay. So there is a maximum height to the ball, right? You throw the ball up in the air, it's going to go up so far, and then it's going to stop and come back down. Okay. So the ball travels downward for t greater than 2 and less than 4 seconds. What happens at t equals 2? Huh? Do what? Yeah. Where is it? Yeah, right. For just one moment, right? At exactly t equals 2, it's not. It just hangs there, right? For just a moment. Okay. All right. So this is the graph. Okay. This S of t is a graph of the height of the ball as a function of time. That is not the flight path of the ball. Okay. So let's draw a schematic, what's called, your textbook calls a schematic diagram of the ball's motion. This is nothing fancy. It's just a visualization of the problem. Okay. So here's the surface of the earth. I can either write ground or earth. Okay. And so the ball gets launched up in the air. It stops for a moment. And then it comes directly back down. That's the flight path of the ball, right? Schematic diagram of the ball's motion, okay? And here's its maximum height. So at t equals 0, it gets launched from the surface of the earth. At t equals 2, it hangs momentarily at its maximum height, and then at t equals 4, it plows back into the ground. Yes, ma'am?
So are we just assuming it's going to land in the same place as them?
Yeah. Yeah. Because it's launched vertically, okay? Now there are in physics, right, problems where the ball is launched at an angle, okay? And then you gotta figure out its maximum height and its lateral horizontal distance it travels and things of that nature. And I have solved those problems. But in here, we're just solving problems where it goes straight up and straight down, okay? It's a very good question. All right. All right, in D, we want to know when is the ball's velocity increasing? When is the ball's velocity increasing? So let's graph the velocity function. It's a function of time. So v of t, I erased it, but v of t is equal to, what is it, 64 minus 32t? What kind of function is that? Linear. And the graph of a linear function is a straight line, right? So here's t equals 0. And so the y-intercept is 64. And the velocity is 0 at t equals 2. So here's t equals 2. And now let's see if I can draw a straight line. Not too bad. So here is minus 64. Right? So at t equals 4, the ball crashes into the ground, right? So v of 4 is 64 minus 32 times 4, which is equal to what? 64 minus 128, which is minus 64, right? Meters per second. So at t equals 0, when it gets launched at 64 meters per second. At t equals 2, when it reaches its maximum height, the velocity is 0. And at t equals 4, this isn't drawn to scale because I'm doing it by hand. At t equals 4, the velocity is minus 64 meters per second. So when is the ball's velocity increasing? For what time? For what values of t? 2 to 4. Now intuitively you know that, right? You throw the ball up in the air and it immediately starts slowing down, right, due to gravity until it stops in midair. And then as it falls down to the earth, it speeds up, right? It increases. So, but you notice that from t equals 0 to t equals 2, the velocity goes from 64 meters per second to 0. So it's slowing down the first 2 seconds. And that goes with your intuition when you throw a ball up in the air. From t equals 2 to t equals 4, the velocity goes from 0 to minus 64 meters per second. Now remember, the sign of the velocity just tells you the direction the ball's going, right? So, from t equals 2 to t equals 4, the velocity goes from 0 to minus 64 meters per second, and so the ball is speeding up. And so the answer is for t greater than 2 and less than 4. Any questions on that? Okay. All right. Oh, so riddle me this. Okay. So from t equals 0 to t equals 2, the ball is slowing down. Why is it slowing down? What's causing it to slow down? Gravity. Gravity is acceleration. So the acceleration, and the reason it's slowing down is the acceleration is in the opposite direction of the velocity. Okay? The velocity is positive, but the acceleration is negative. It's going in the opposite direction. Okay? The reason it's speeding up from t equals 2 to 4, okay, is the acceleration and the velocity are in the same direction. And so that causes speed even though the velocity is negative. So the acceleration is also negative. So the sign of the acceleration just tells you the direction of the acceleration. Okay. So we can do a little diagram to show when an object is speeding up and when an object is slowing down. So the velocity of an object can either be positive or negative. And the same is true with the acceleration. It can be either positive or negative. The sign of the acceleration just tells you the direction of the acceleration. Okay. So when the velocity and the acceleration are both positive, they're both in the same direction, and so the object is speeding up. And the same is true when the velocity is negative and the acceleration is negative. They're both in the same direction, and so the object will speed up. When the velocity is negative and the acceleration is positive, they're working in opposite directions, and that'll cause the object to slow down. And the same is true when the velocity is positive and the acceleration is negative. They're working in opposite directions, and so the object will slow down. Now when we do an object that is moving on a straight path left and right, you'll see how that works. Okay? That when the object is moving in one direction but it's slowing down, that's because the velocity and the acceleration are in opposite directions. Okay? All right. The balls, so this defines speed versus velocity. So velocity can be positive or negative. Does anybody know what the definition of speed is?
The absolute value of velocity?
Yeah. We don't care about the sign, right? So in the definition of speed is the absolute value of velocity. Which we use v of t for its function. Okay? So when we talk about 55 miles per hour, we're not specifying right, that doesn't tell us what direction we're going. Okay. All right. In F, we're going to graph the ball's speed. So we graph the ball's velocity function over here. So when we graph the absolute value of v of t, for those of you who had pre-calculus with me, we did graphs involving the absolute value. When we take the absolute value of v of t, this part, anything that's below the x-axis gets flipped above the x-axis, right? Because the absolute value is always positive. Right? So the graph of the ball's speed. Here, right, oh, there's no x-axis. T-axis, and then we have the absolute value of v of t. And so from the graph over here, we know from t equals 0 to t equals 2, right? The graph is above the t-axis. Okay? So that doesn't change, okay? Velocity is positive from t equals 0 to 2, right? So speed is positive, right? That's also the graph of speed. But for t equals 2 to 4, the velocity is negative and speed is positive, right? So the absolute value of the velocity function of t equals 2 to 4 flips that part of the graph above the t-axis. And so that's the graph of the ball speed as a function of time, right? All right, any questions? All right, one more part. When the ball is speeding up, when is the ball speeding up and when is it slowing down? Well, we already sort of answered that question over here, didn't we? When is the ball, actually I'm going to erase this. When is the ball speeding up? And when is it slowing down? And now we sort of answered it over here. We can answer it from over here with the speed graph, right? From t equals 0 to t equals 2, the speed goes from 64 to 0, right? So it's slowing down from t equals 0 to t equals 2. And when is it speeding up? Well, from t equals 2 to t equals 4, the speed goes from 0 to 64. And we had the same results over here, just looking at the velocity function, right? Velocity go from 64 to 0, right? Means it's slowing down. And when the velocity goes from 0 to minus 64, it means it's speeding up. Okay? So you get the same result from both graphs. Okay? All right, so that's an example of rates of change in the sciences. So now we're going to do another example, but not with the ball thrown up in the air. We may not finish this one in 26 minutes. We may have to finish it tomorrow. Okay, so in this case, in this example, right, we have a number line, and we have an object moving back and forth on the number line, okay? Or you can imagine that you're out in the country somewhere on a straight road, and you can either drive your forward or backward, right? Forward or backward. All right, so an object traveling along a number line has its position S of t equal to 1/4 t to the fourth minus 2t squared, okay? So that's a 4th degree polynomial, okay? An object traveling along a number line has its position S of t equals 1/4 t to the fourth minus 2t squared meters at time t seconds. So here's 0, 1, 2, 3, 4, 5, minus 1, minus 2, minus 3, sorry, on the number line, okay? So at t equals 0, so we're going to assume that time starts at 0, okay? At t equals 0, where's the object located at, right? It's you in your car on a straight road. Well, at s of 0, we have 0. So here's the location of the object at position 0 at t equals 0. Okay, this is not a timeline. This is the line for S of t. This is where the object is located on this number line. Okay. At t equals 1, and you guys can verify, check my math. S of 1 is equal to minus 1.75. So here's minus 1.75 on the number line. So from t equals 0 to t equals 1, the object goes from here to here. Okay. At t equals 2, the object is at minus 4. So here's minus 4 on the number line. So that's where the object is at t equals 2. At t equals 3, the object is at 2.25, which is about right here. So this is where the object is t equals 3. So from t equals 2 to t equals 3, it went from position minus 4 to 2.25 on the number line. And then lastly, at t equals 4, the object is at 32, which is way out here somewhere, okay? So this number line tells you, gives the location of the object, okay, at various points in time. Okay. Are you following me with this? This is not a timeline, okay? This is the location of the object, okay? So if this is you on a straight road in your car going forward or backward, this is the position of you in your car on that road at various points in time, okay? All right. In A, we're going to find the object's velocity, acceleration and speed. Well, we've done this already. Velocity is the derivative of the position function, s of t, which in this case is equal to t cubed minus 4t. The acceleration, a of t, is the derivative of the velocity function, which is the second derivative of the position function. And a of t in this case is equal to 3t squared minus 4. The speed function is absolute value of the velocity function, right? So speed is the absolute value of the velocity function, which is the absolute value of t cubed minus 4t. Okay? Hope we're all in agreement. When is the object moving? In the positive direction. Well, which way is the positive direction? To the right, correct? So how do we find when the object is moving in positive direction, to the right? But it has to be true.
V more than 0.
Say what?
V more than 0.
What's more than 0?
Velocity.
Velocity, right? So velocity tells you the direction you're going, right? And so the velocity is positive when you go to the right. It's negative when you go to the left. Okay. So to find when the object is moving in the positive direction, we set the velocity v of t greater than 0. So what's v of t equal to? T cubed minus 4t. Now what do we do?
Take out a t.
Do what?
Take out a t.
All right, take out a t. T times t squared minus 4. Now what do we do?
T minus 2, t plus 2.
Say what?
T minus 2.
Oh, you factor t squared minus 4. Okay. So we have t minus 2 times t plus 2
And we set all of those equal to 0.
is greater than 0, right? Now what do we do?
Set them greater than 0 individually. No?
My students do that on pre-calculus exams and drives me crazy. But sometimes they get the right answer and sometimes they don't. Well, this is called a polynomial inequality. And we do cover this in pre-calc. And so you have to do what is called the test point method, or the sign chart method to find the values of t that make the left-hand side greater than 0. Okay? And so, how do you do that? So for those of you who had pre-calc, this should be reviewed, right? Who had pre-calc here at College of Charleston. Okay. So the first step is make sure you got 0. So this, let me rewrite this. So this is a polynomial inequality. And so you were right about the factoring. We needed to factor first, the left-hand side, okay? The second step in solving this is to set each factor equal to 0. So we got t equals 0, t minus 2 is equal to 0, and t plus 2 is equal to 0. And you solve each of these for t. You get t equals 2, t equals minus 2. And then you use those values of t to break the real number line up into intervals. So, got minus 2, 0, and plus 2. Now, what is unique about this problem is we're not interested in all values of t that make the left-hand side greater than 0. We're only interested in values of t, positive values of t, that make the left-hand side greater than 0, because time starts at 0. Okay? So we don't care if negative values of t make the left-hand side greater than 0, because we're not interested in negative time, only positive time, starting at t equals 0. Okay? So we can ignore this guy out here. And just do from t greater than 0. Okay? Well, t equals 0 is not in our solution set, so I'm going to put an open circle there, because t equals 0 makes the left-hand side equal to 0, and 0 can't be greater than itself. And the same is at t equals 2. I'm going to put an open circle there, because t equals 2 makes the left-hand side equal to 0, and 0 can't be greater than itself. Okay. So we really got only 2 intervals to test to see if any, the numbers in either of these 2 intervals, right, result in a positive velocity. Okay. The velocity is positive in either of those 2 intervals. And so with the test point method, if for one value of t in this interval, if the velocity is positive, it's positive for all values of t in that interval. If it's negative for one value of t in this interval, it's negative for all values of t in that interval. Right? That's the test point method or the sign point method. Okay. So 1 is between 0 and 2, right? Testing this interval. So t equals 1 is my test point. And it doesn't matter whether you use the factored form or the unfactored form. You just want to know, is the left-hand side positive or negative with that value of t. So if I put 1 in for t, I have 1 cubed minus 4 times 1, which is equal to 1 minus 4, which is negative 3. That's a negative number. So any number greater than 0, less than 2, makes, put in for t here, makes the left-hand side less than 0, not greater than 0. So the velocity is actually negative from t equals 0 to 2. And that means that the object is moving to the left because the velocity is negative. And we saw that from t equals 0 to t equals 1 to t equals 2, the object moved to the left. Okay? So that goes with what we already knew. Okay? Now this second interval, for t greater than 2, 3 is greater than 2. So when I test t equals 3, and I put it in here on the left-hand side, I have 3 cubed minus 4 times 3, which is equal to 27 minus 12 is what, 15? 15 is a positive number. So any number greater than 2 put in for t over here makes the left-hand side greater than 0. So that tells me that the velocity is greater than 0 or positive for all time t greater than 2 seconds. Okay? Is it seconds? Yeah, seconds. Okay. So when is the object moving in the positive direction to the right? For t greater than 2 seconds, which in interval notation, you know, is 2 to infinity. You understand that? Okay. And it kind of agrees with what we did over here. From t equals 0 to t equals 2, the object moved to the left. And now, for t greater than 2, the object moves to the right forever on an endless road. Okay. All right. So let's draw a schematic graph of this object's movement. So we redraw the position right, I'm just redrawing what we have up here, S of t, right, the number line for S of t. So here's 0, 1, 2, 3, 4, 5, minus 1, minus 2, minus 3, minus 4, minus 5. And I'm not going to draw on the number line, because if you go just draw stuff back and forth on top of the number line, you can't make anything out. But at t equals 0, we're at position 0. And then at t equals 2, we're at position minus 4. So above the number line, okay, I can connect the point at t equals 0 to the point t equals 4 and put arrows to indicate the object, right, started here at t equals 0, or at position 0, and went from here to here to position minus 4, okay, 2 seconds later. This is t equals 0, this is t equals 2, this position, okay? And then it didn't make a U-turn per se, it just stopped and then went back to the right, okay? But as a diagram, we're going to make it look like it made a U-turn. And then it went to the right forever. Now this is actual movement on this number line, right? It started here at t equals 0, went to the left, right? Started here at position 0 at t equals 0, moved to position to the left of position minus 4 in 2 seconds, and then it's going to the right on this number line forever after the first 2 seconds. Okay. But I draw that movement to the left and to the right above the number line, right? Otherwise, you're drawing stuff on top of each other and you can't make it out. Okay. So that's what a schematic diagram looks like for this situation. Okay. All right. So we will finish up the last 2 parts of this problem first thing tomorrow. Okay. And then this homework will be due Monday night.